Welcome to Zaption Tour 6.5, Linear Inequalities. There are 6 boxes. Consider the following 3 questions. I'm going to ask you these one at a time. Number 1, I want you to think of 2 different numbers such that when you add them together, their sum is more than 10. Question number 2, how many different pairs of numbers do you think there are? How can you tell? Number 3, how could you use algebra notation to express this quantity? What can the graph tell us? For simplicity's sake, I just said let's let everybody make sure that x and y are the 2 different numbers. Hopefully you got the answer of x plus y is greater than 10, and there are infinitely many ways that this can occur. This leads us right into the fact that we're going to be talking about linear inequalities. And what makes this an inequality is the fact that there is a greater than or a less than sign hidden within the inequality itself. It's no longer just an equal sign. Box number 1 is an example. It says, is the ordered pair a solution to the linear inequality? How can the graph support your answer? Well, we do exactly what you think you would do here. So I have an ordered pair 1, 2. So I'm going to take the 1 represents the x and the y represents the 2. So I'm going to substitute back into the inequality and see. So is 2 greater than 1 minus 3? So is 2 greater than 1 minus 3 is negative 2. Is this a true statement or is this a false statement? Well, this would be a true statement because 2 is bigger than negative 2. Let's take a look at this one here. If I substitute in, is negative 7 greater than negative 3 minus 3? So is negative 7 greater than negative 6? Well, no, this is false. And remember, this is false because of the way the number line works, right? If this is the number 0, then this is the number negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. Well, here's negative 7. Here's negative 6. Negative 6 is bigger than negative 7 because it's closer to 0. So this will be a false statement. So negative 3, negative 1 is not a solution, but 1, 2 is a solution. And it says, how can the graph support your answer? Well, let's take a look at the graph. All right. So here's the graph right here. If I go ahead and graph this, what we're going to see is we're going to have a region. We're going to have a certain region that's colored in. Okay, so you can see everything that is sort of above this line. And by the way, this is the line y is equal to x minus 3. But notice that the line is dashed because of the fact that it has to be strictly greater than. So if I graphed the point, 1, 2, and negative 3, negative 7, if I graph the point 1, 2, you'll notice that this point is inside the shaded region. But if I graph the point negative 3, negative 7, you'll notice that this point is outside the shaded region. Therefore, it's not a member of the solution. So everything that's in the shaded region represents a member of the solution set. This is why there are infinitely many answers. Box number 2 is an example. Let's graph the linear inequality together. It says y is greater than x minus 2. So what you want to do first is just consider that this will be the graph y equals x minus 2. So you got to ask yourself, how would you simply graph that one? Well, the y-intercept is negative 2, so I'd go down to negative 2, and the slope is 1. So I would go up 1 and over 1, up 1 and to the right 1. Now, because this graph is an inequality, it's greater than, so I have to make the line in a dashed fashion like this. And the reason it's a dashed fashion is because none of the points on this line can actually be a member of this graph. So it must be a dashed fashion. And then I want to take you'll notice that there are 2 regions here. There is a region above the line, and then there's a region sort of below the line. And what I want to do is figure out which region makes this inequality true. So I like to use the test point 0, 0. So is 0 greater than 0 minus 2? Is bigger greater than negative 2? That answer is a true statement. So therefore, we're going to shade the region of the true statement. So we would shade all of this area, and you can just use your pencil and shade it in like this. So I'm going to graph it to check it and see, make sure I did it right. y is greater than x minus 2. So I'll come over here and graph it. I'll say y is greater than x minus 2. We'll put the graph up here and we'll see, yep, my picture just looks like this picture here, so I must have done it right. I'm going to show you how to do this on your calculator in class. Okay, box number 3 is an example. I'm giving you two lines here, one's vertical, one's horizontal. So part A says, let's graph the inequality x is greater than negative 1. So here's negative 1 on the x-axis, and we're going to do a vertical line, and the line has to be dashed because it says greater than, so I cannot include any member of that line there. And I want to shade to the right because it says greater than that. So this is what my solution set would look like for x is greater than negative 1. Y is less than negative 2. Well, I'll go down to negative 2 on the y-axis. I would put a solid line in this particular case because the line is a member of the solution set. So notice the difference between those two. And I want everything that's less than that. So everything below the axis would represent the graph y is less than or equal to 2. So let me show you how these would look on the graph to check. So here's the first one. And notice that the line is dashed. I want everything to the right. And here's the second one. Notice that the line, oh, this should be negative 2, excuse me. Notice that the line is solid and it's everything below that line. Box number 4 is an example. It says write the linear inequality shown below. So I have a region here that's shaded, and I have a line that is dashed, and then I have a region that's unshaded. So the first thing I want to do is consider, okay, I know that if I was going to just graph this line, it would have to be y equals mx plus b. All right, then I want to figure out what the slope and the y-intercept are. Well, the y-intercept is clearly 1, so I'd have y is equal to mx plus 1. And then the slope of this line looks like it's also 1, because to get from here to here, I would go up 1 and over 1. Remember, that's the ratio of slope, rise to run. So it looks like I would have y would be equal to x plus 1. Now, because I have a shaded region, I need to create an inequality. So I'm going to take the test point 0, 0, and I would guess that my inequality would be a less than. So I would say this, y is less than x plus 1. Notice that I have just strictly less than because the line is dashed. I'm going to take a test point and see if this is actually true. Take my test point. So is 0 less than 0 plus 1? Is 0 less than 1? Is that true or false? Well, that's true. So that tells me that this is the correct way to write the inequality. Notice if I said it the other way, I'd get a false statement. What if I said y was greater than x plus 1? So is 0 greater than 0 plus 1? Is 0 bigger than 1? No, that's false. So that would tell me that this inequality sign was the wrong direction. That's how I know that this one is the correct answer. Always use 0, 0 if you can to test your point to figure out the direction of the region. Box number 5, another example, same idea. Write the linear inequality shown below. Okay, so I'm going to start assuming I had a line. So y would equal mx plus b. I look at my line here. The intercept is negative 3. So y is equal to mx minus 3. And the slope of this would be up 3 and over 1.5. So that'd be 3 halves. So y is equal to 3 halves. I'm sorry, it's not 3 halves. It's y is equal to up 3 divided by 1.5, which is a value of 2. Because 3 divided by 1 divided by 3 halves gives me a value of 2. Anyways, we can clearly see that by going up 2 and over 1. So anyways, so back to the problem. So y would equal 2x minus 3. Okay, that's if I had the line here. But I don't have a line, I have an inequality. And notice that the line of my inequality is solid. So it would be y would have to be greater than or equal to or less than or equal to. I'm going to go ahead and assume that it's greater than or equal to because it's above the line and see what happens. Okay, 2x minus 3. So let's test this point to see if I got this correct. So I'm going to go ahead and use the point 0, 0. So is 0 greater than or equal to 2 times 0 minus 3? So is 0 greater than or equal to 0 minus 3? Is 0 greater than or equal to negative 3? And that is a true statement. 0 is bigger than negative 3. So therefore, this would be the correct answer. Again, what if I didn't know that? What if I accidentally made a mistake? What if I said that 0 was less than or equal to 2x minus 3, and I took a test point 0, 0? So 0 is less than or equal to 2 times 0 minus 3. Is 0 less than or equal to negative 3? No, that would be a false statement. So that's how I know my inequality direction is correct, of y is greater than or equal to 2x minus 3. Okay, box number 6 is a U-try. Write the linear inequality shown below. I've given you a couple of things to remember here written down on the right-hand side. Is the line solid or dashed? What's the slope? What's the y-intercept? Determine the inequality using an easy test point. Hopefully you got the right answer. If not, here's the solution. The line should be a dashed line, so therefore my inequality should just be greater than or less than, not greater than or equal to or less than or equal to. The slope of the line is 1, because I go up 1, I go over 1. And the y-intercept is a value of 2. So putting this all together, you would have y is greater than x plus 2.